Bismillahirrahmanirrahim. So we have been given this giant PDF random variables x and y, and we are supposed to find whether x and y are independent or not. So let us begin working the solution to this problem. So random variables x and y are independent if and only if the giant PDF fxy x comma y is equal to the product of their individual PDFs, right? If this condition holds true, then the random variables x and y are independent, and this is the necessary and sufficient condition for the independence of random variables x and y. So to establish whether this condition is true or not for the given joint PDF, we first need to find the marginal PDFs of random variable x and random variable y. So the marginal PDF of random variable x, for example, is given by this integral from minus infinity to plus infinity, and fx comma y x comma y and dy. We integrate out the random variable y from the joint PDF to obtain the marginal PDF of a random variable x, right? So we have this PDF here for the non-zero region, and we first need to also determine the region of non-zero region of this giant PDF here. So it's given that x, this PDF is has this value for this region: x greater than 0, y greater than 0, and x plus y less than or equal to 1. Let's plot this region. So for example, we have it here. This is x and this is y, and you see that x greater than 0 means this region, right? And y greater than 0 also means this region, right, above x-axis. And this is the region here, the first quadrant, that x is greater than 0 and y is greater than 0. But we have a third constraint also, which means x plus y is less than or equal to 1. So how do we determine this region? To determine where x plus y is less than or equal to 1, we first need to find out x plus y is equal to 1, the region, the line x plus y is equal to 1, right? So this must be a straight line. It could be written like that: y is equal to 1 minus x. So when x is equal to 0, y is equal to 1, right? X is equal to 0. This is x is equal to 0 and y is equal to 1 here. And when y is equal to 0, right, when y is equal to 0, x is equal to 1. This is x is equal to 1. So this straight line can be drawn like this here. So it is now easier to find the region of where x plus y is less than or equal to 1. Let's label this line. This is x plus y is equal to 1, this line. So when the combined values of x and y are less than 1, then only then they could be equal to 1, right? Or they could be less than 1. So it is this region here where the values of x and y are less than, both less than 1, where this condition holds true. So x plus y is less than 1 in this region. So this is our region of interest here. This is the region where the joint PDF is non-zero. So this will also help us determine the limits of our integrals when we integrate to find out the PDFs, marginal PDFs of random variable x and random variable y. So let's begin. Fx of x is given by the value of the PDF 24 xy, and we are to integrate with respect to y, right? And we are to integrate over the entire range of y. So y is If, for example, we take an arbitrary line here for y, like here for example, and this line, it has y is equal to 0 here, and here at this point, for example, y is equal to 1 minus x, right? So the limit for y are y is equal to 0 to y is equal to 1 minus x. The limits should be in terms of x, because we are to determine the PDF for random variable x. So this is 24x and y square over 2, right? So this is 2 and this is y square, and these are the limits 1 minus x. So fx of x is equal to 12x into 1 minus x square. So this could be written like this, the entire complete PDF, 12x into 1 minus x square for x is 0 to 1. X is greater than or equal to 0, less than or equal to 1, and this is 0 otherwise. So this is the PDF for random variable x. Likewise, we can find the marginal PDF of random variable y. Fy of y is given by minus infinity to plus infinity fx comma y, x comma y, and dx. We are now to integrate out the random variable x from this joint PDF to find the marginal PDF of random variable y. So fy of y is given by this is 24 xy and dx, and the x will vary now from here to here. X is 0 here, and x is, in terms of this equation, x is 1 minus y here. X is 1 minus y here, for example, right? So this is 1 minus y. So fy of y is 24 y, and this will be x square over 2, this is over 2, this is x square, and 0 to 1 minus y. So fy of y are 12y into 1 minus y square, right? So in summary, the PDF of random variable, marginal PDF of random variable y is given by 12y to 1 minus y square for y is greater than 0, less than or equal to 1, this is 0 otherwise. So we have determined the marginal PDFs of random variable x and random variable y. So we can see that it's the product of the PDFs is not equal to the joint CDF. We can see that fx comma y, x comma y is not equal to fx of x multiplied by fy of y, right? So for example, the product, this 12 multiplied by 12, 144 xy, then 1 minus x square, 1 minus x whole square, and 1 minus y whole square. This does not turn out to be equal to 24xy. So we have this condition here that fxy, the joint PDF, is not equal to the product of the individual PDFs. So x and y are not independent, right? X and y are not independent random variables. So this is the conclusion we can draw from our calculations so far. Now it will be interesting to find out the covariance of these random variables and to see whether these are correlated or not. If the covariance is 0, then the random variables are uncorrelated, right? And when the covariance is not 0, then these are uncorrelated, right? So the covariance, the formula for the covariance of the random variables x and y is given by, for the expected value of this function, x minus mu x multiplied by y minus mu y, right? So to find the covariance, we need to make certain other calculations. For example, covariance xy is also given by, actually this is equivalent to this xy, expected value of xy minus product of the expected value of x and expected value of y, right? So we need to determine these three quantities to determine the covariance of random variables x and y. So for example, the expected value of x is given by this integral minus infinity to plus infinity. So x multiplied by fx of x dx here. So expected value of x, which is also represented by mu x, is given by x multiplied by this here 12x into 1 minus x square, right, and dx, and the limit is from 0 to 1. So expected value of x is, this is 12, we can take it out, and this is x square, right, into 1 minus, this is 2x plus x square dx, right? So expected value of x is given by 12, 0 to 1, this is x square, we multiply this minus 2x cube plus x raised to the power 4, and this is dx, right? And expected value of x then here is given by 12, and this is x cube over 3 minus 2x raised to power 4 over 4 plus x raised to power 5 over 5, and the limit is from 0 to 1. So let me reproduce it here also. Expected value of x is equal to 12 and x cube over 3 minus 1 over 2 x raised to power 4 plus x raised to power 5 over 5, and the limit is from 0 to 1, right? So expected value of x is 12 into 1 over 3, we put the limits in them, this 1 over 3 minus 1 over 2 plus 1 over 5 and minus 0 will be, right? So expected value of x is 12, and what will be the LCM? The LCM will be 5 into 6, 30, right? So this is 3 into 10, 10 minus 15 plus 6. So expected value of x is given by 12 over 30 into 10 plus 6, 16 minus 15, 1. So this is 6 into 12, 6 into 5, 2 over 5. So expected value of x, or mu x, is 2 over 5, right? Similarly, we can also find the expected value of y. So expected value of y is given by minus infinity to plus infinity y, fy of y, and dy, right? So expected value of y is y, and the PDF of y, let's have a look at this, is 12y 1 minus y square. If you look carefully, the PDF of y and the PDF of x, they are quite same, only the change of variable, right? 12x and 1, if you replace x with y here, so this will be the PDF of y, and the range is also same, 0 to 1, right? So we are now evaluating integral similar to the one we have already evaluated here, right? So if we write, for example, let me write it down here, y and 12y into 1 minus y square dy 0 to 1. This is the same integral that we wrote here, right? So it will evaluate to the same value here. So expected value of y, mu y, is also 2 over 5. Now we are left with only one more value to evaluate, which is expected value of xy. This is also called the correlation of the random variables x and y, right? This is also called the correlation of x and y, and this is given by this double integral xy here for xy, and then we have fx comma y, x comma y, dx dy, right, from minus infinity to plus infinity, from minus infinity to plus infinity. So expected value of xy is given by, so xy, and our PDF, our joint PDF is given by 24xy, right? So 24xy dx and dy. So the important step here is to determine the limits of this integral. We are integrating first with respect to x, so these are the limits for x and these are the limits for y, right? So we are integrating over this region here now, right? And we are integrating first with respect to x. So this is the strip here from x is 0 here, right? And it goes on till here, and as we have discussed here before, x is equal to 1 minus y here, 1 minus y, x is equal to 1 minus, so 0 to 1 minus y. The limits of x are from 0 to 1 minus y, 0 to 1 minus y, and this strip will move from we will move y from 0 to 1 over this entire region to cover this entire region. So the limits for y are 0 to 1, right? So let's proceed. Xy is 24. This is xy square now, x square and y square. X is equal to 0 to 1 minus y, and y is equal to 0 to 1, and dx and dy, right? So expected value of xy is equal to 24, and y is equal to 0 to 1, and if we are integrating with respect to n, then this will be x cube over 3. So let's take 3 out here, x cube over 3, right? And the limits would be from 0 to 1 minus y, and we are still left with y square and dy, right? So expected value of xy is 8, and then 0 to 1, y is equal to 0 to 1, then we have y square into 1 minus y cube dy, right? So expected value of xy is equal to 8. This is y 0 to 1. This is y square. Let's expand this. This is 1 minus 3y plus 3y square minus y cube. 1 minus y cube is expanded to this expression. This is 1 minus 3y plus 3y square minus y cube, and this is dy here. So expected value of xy is 8. This is 0 to 1, and let's multiply this. Y square minus 3y cube plus 3y raised to the power 4 minus y raised to the power 5, and dy, right? So now this is easier to integrate this individual expressions. So this is 8 here, and this comes up to be y cube over 3 minus 3 over 4 y raised to the power 4 plus 3 over 5 y raised to the power 5 minus y raised to the power 6 over 6 and 0 to 1, right? So expected value of xy is given by 8, and we're putting the limits now. This is 1 over 3 minus 3 over 4 plus 3 over 5 minus 1 over 6 and minus 0, 0, 0, right? So here we are, expected value of xy, or the correlation of x and y, is 8, and what should be the LCM? 6, 5, 4, 3, 6 multiplied by, this is 60, right? So 20 into 3 is 60, minus 4 into 15 into 3 is 45, 5 into 12 and 12 into 3 is 36, and sorry, this is minus here, minus 10. So expected value of xy is 8 over 60 into 20 plus 20 minus 10. It will be 10, right? 20 minus 10 is 10, and 10 plus 36 is 46. 46 minus 45 is 1. So this is 1 here only, right? So this will be 4 into 2, 8, 4 into 15, 16. So 2 over 15. Expected value of xy, or the correlation of xy, is 2 over 15. So this is not equal to 0. Hence, x and y are not orthogonal. Had this been 0, this expression, we could have said that random variables x and y are orthogonal. Okay, so now we can determine the covariance. So covariance of x and y is equal to this expression. So this we have already determined here. So covariance of x comma y is 2 over 15 minus the product of the mean values of x and y. So mean value of x is 2 over 5 and the mean value of y is 2 over 5. So this is 2 over 5 into 2 over 5. So covariance of x comma y is 2 over 15 minus 4 over 25, right? So covariance of x comma y, sigma xy, is let's take some LCM. LCM is 25 into 75. This is 5 into 2, 10, minus 25 into 3, 3 into 4, 12. So covariance of x comma y is minus 2 over 75. So the covariance of x and y is a negative quantity. So, but this is not 0. Hence we can say that the random variables x and y are correlated. Random variables x and y are correlated, right? So we have already concluded that random variables x and y are not independent, and we have also found out that random variables x and y are not orthogonal, and random variables x and y are also correlated. Okay, so that's it.